I will describe the tau performance system. I'll show you some hands-on exercises on theta. And I hope you all have accounts working on theta so you can kind of follow along. You can also download these slides from this place as well as our AppSec web page so you can follow this. So the tau performance system is a mature profiling and tracing toolkit that has evolved over the last 20 plus years, and it supports instrumentation, measurement, and analysis components. In this particular talk, I would like to take some time and describe some key features that are common to many performance evaluation tools. So if you look at the performance data from one tool, you can understand how it was generated, what performance model it includes, and you can get a better understanding of any of these tools. So instrumentation is the process of adding hooks to your code, and you can do it in a variety of different ways in Tau. I'll describe some of them, and once those hooks are inserted, you can choose what gets measured. Whether you generate profiles, whether you generate traces, whether you use hardware performance counters or not, and then you can analyze the data. For profiles, you can use our tools such as Paraprof to view it, and for tracing, you can use JumpShot, you can use Vampire, you can use even the Chrome browser to look at the trace files. I will describe some of these aspects of Tau, but I would like to just take a minute and say that if you have a program that is written in Fortran or C or C++ or UPC or even Java or Python, and you have a combination of languages, you can use Tau to understand its performance. You can automatically instrument the source code. You can automatically instrument it at a variety of different levels. And one of the most important locations where you can insert these hooks is at the runtime. If you have an MPI or a pthread or an OpenMP runtime, it's very easy to insert hooks at the runtime without modifying the application binary. And we'll look at some examples of this. We have a support for MPI, OpenSHMEM, RMC, PGAS runtimes, even DMAP in Cray, and a variety of different threading models, as you can see. If you have GPUs, Tau can support instrumentation at the level of CUDA using the CUDA profiling tools interface. It can do instrumentation at the OpenCL level or even the AMD ROCm, and we support both Rock Tracer and Rock Profiler APIs in the version that's shipping. So you can use this to transparently measure the time the application takes at the runtime level, whether it's OpenACC or OpenCL or a combination of these runtimes. And you can generate profiles as well as traces. We also have a tool called Perf Explorer, where you can do cross-experiment analysis, you can do clustering analysis, we can store the performance data in the TauDB database, so you can compare different experiments using the Paraprof and Perf Explorer tools. Paraprof includes a 3D profile browser, and I may be able to show you a demo of that as well. So you're probably wondering at this stage, what is it that Tau can do for me? What is it that, what kind of performance evaluation studies can I conduct with Tau? So first of all, Tau can tell you how much time is spent in your code regions. It can show you at the routine level, at the loop level, outer and inner loops, even at the statement level. You can see how much time was spent in each of these code regions. Instead of time, you could substitute time with hardware performance counters as well. So you could use counters from PAPI or Liquid and see the metrics such as how many instructions were executed in this code region, how many level 1 data cache misses took place, how many floating point instructions took place, what was the extent of vectorization, and so on. You can look at the memory usage of your code. Where does memory get allocated, deallocated? What is the high water mark of memory usage? What is the max memory that my process used? You can look at the energy usage of your application, even the I/O characteristics of your code, such as which files did my application access? How much data did it transfer? What was the read bandwidth? What was the write bandwidth for each file? You can see the contribution of each phase of your program. You can also see how the application scales and what is the efficiency, runtime breakdown at different core counts. So to do all this, you need to first of all add hooks to your code. And you can do this at different levels. So the first level is the source instrumentation. Now we've all done source instrumentation ourselves at some point in time, right? You've got a loop and you say T1 equals get time of day. There's a for loop. Then you say T2 equals get time of day. And then there's a print statement that says time spent in the loop is T2 minus T1, right? Those do-it-yourself approaches are quite common, but they don't necessarily scale. And we have source instrumentation tools which can just take a full source file and rewrite it with the entry-exit instrumentation at the routine level or the loop level, inserted automatically in a copy of your source file. You can also use a selective instrumentation filter file where you can say instrument this or don't instrument this. You use Tau compiler scripts such as taocc.sh or taof90.sh to substitute the MPI compiler with this Tau shell script, and then you can generate object code, even link in libraries and create an executable and run it to generate the data. Instead of source instrumentation, we can use compiler-based instrumentation where the compiler itself adds hooks in your code. Now we have done quite a bit of work with integrating with LLVM where we can do instrumentation on a set of functions by creating a Tau plugin that resides inside the compiler or is loaded during compilation. We can also use the compiler-based instrumentation in compilers like Cray or Intel or PGI and GNU and so on. We can do preloading a dynamic shared object from Tau. And this is a very interesting approach that I'll show you. Now with preloading, what I do is I take a shared object and I load it into the memory before the application is loaded. And whatever functions are defined in this shared object, they take precedence. So if your application calls MPI send and I preload the Tau library, then the application will call Tau's MPI send, which will internally call the system MPI send while adding hooks to the start and stop timers around that function call. So now we have a way to transparently execute an MPI application where I did not need to change anything. I take a dynamic executable and instead of saying ap run a.out, I can say ap run TaoExec a.out and I can see all the time spent in MPI calls. We can also do this for other runtimes, whether it is CUDA or whether it is ROCm based runtimes or OpenMP. We can insert hooks at pthread, OpenMP, OpenACC, a variety of different levels. So you can now see the time spent in the rest of your runtime code precisely with start and stop timers. The only issue is that it only works with dynamic executables. So if you are using the stock compiler scripts on Theta, you should just add the -dynamic flag while linking. Now Tau can generate profile files as well as traces. Profiles can show you the total contribution of the code regions, the summary of the statistics. So if there is a function like MPI barrier that gets called 20 times, then at the end of the program, the tool will emit a single line saying MPI barrier was called 20 times, it spent 50 seconds in this function. Tracing, on the other hand, will generate a time-stamped log of events. So there is an entry event with a timestamp that says MPI barrier entry took place at this time and exit took place at that time. So there is a detailed trace log which can allow us to represent the performance along a timeline view. So you can see what every process over here is doing at any given point in time. But it generates a lot more data, as you can imagine. So profiling is always a good first step, and to reduce the overall instrumentation to only those parts that are relevant, and then you can do the tracing and generate detailed trace logs. This is the jump shot trace visualizer, which comes from the Argonne National Labs, and I would like to thank them for allowing us to include it as part of Tao. And you can use Paraprof and jump shot together. Now with profiling, one of the things that you will be able to generate with any of these tools is a precise calculation of inclusive and exclusive time. By inclusive and exclusive, what I mean is, consider there is a function called foo, and say it spends 100 seconds in foo. So the green part over here shows you the total time from the beginning to the end of foo when we have timers inserted at the entry and exit of foo. And if it calls a function called bar and say it takes 20 seconds in bar, then you could say that the time spent exclusively in foo is 80. Okay, the time in foo outside of the child calls that are over here. So this is a very important distinction. You want to see what is the time spent in that function. And to add the hooks, you can either add it directly by probes, where you have a start and stop call, and that computes the exclusive and inclusive time precisely, or you can do it indirectly using sampling, where a periodic interrupt is generated, and you look at the state of the program and where it is executing, and based on that, you can create a summary and estimate where the application is spending its time. So here is an example of sampling where an interrupt is generated either by a wall clock timer, where you could say every 50 milliseconds generate a time interrupt, and then you can estimate based on how many interrupts you got and the total execution time where the time was spent. Instrumentation, on the other hand, requires code to be inserted directly in the source, like the start and stop, and then you can calculate the precise exclusive and inclusive time. So those are the two broad categories of tools. At the highest level, profiling tools or tracing tools. In profiling, you can have sample-based tools or tools that use direct instrumentation via probes. So Tao does both profiling and tracing and supports both sampling as well as instrumentation. But using Tao, you can use a tool called TaoExec, which can help you track the time spent in different runtimes as well as enable sampling. Your application time spent in MPI, OpenMP, POSIX.io, memory allocation, deallocation, wrapper libraries for external libraries, they can all be instrumented using TaoExec, and then you don't need to modify your binary executable as long as it is a dynamic executable, because we are injecting a shared library, a shared object. And so that requires a dynamic shared object, requires a dynamic executable. And once you use this TaoExec, you can enable other Tao options, such as generating a communication matrix or generating OTF2 traces for a tool such as Vampire, or enabling event-based sampling. Okay? So one of the important features of Tao is that it does support OpenMP instrumentation. Now, as John mentioned earlier, there's quite a bit of work that's been going on for a simple question that tool developers have always said: can you give us an event when important events take place inside the OpenMP runtime? If there is a parallel for, or there is a synchronization operation, or key events or actions that take place inside the OpenMP runtime, can you make those actions visible to the tools without our requiring to go inside the runtime and add those calls manually? So they have done quite a bit of work with an initial Intel OpenMP runtime that was open source, and that was then subsequently taken into this LLVM project, and John's group has contributed significantly to the development of the OpenMP instrumentation capabilities, which are now available, and the compilers have added support for the OpenMP tools interface. So as it has evolved, earlier we had support for the OpenMP TR4, Technical Report 4, TR6, and more recently the TR7 with Intel compilers, and finally the version 5 of OpenMP tools interface, where you do not need to substitute one runtime with another, but the tool itself provides all the hooks. The compiler itself integrates with the tool and makes those OpenMP events visible to the tool. So now we can just launch an uninstrumented MPI with OpenMP binary with TaoExec and then observe the time spent in all those OpenMP regions. Not only that, we can also see the time spent in the rest of the code using event-based sampling. So this is an example of where you may want to use two different approaches. One, to insert hooks at the MPI and OpenMP level, and second, to enable the generation of those interrupts so that you can measure based on event-based sampling. So I'll show you a demo of this, but let me just say that this is how we use Tao. So if you have a dynamic executable, say a.out, you could say ap run minus n64 a.out to run it. If you just want to track MPI level statistics, you could just say TaoExec a.out. You could say TaoExec-ebs a.out to generate event-based samples. Now see, between these two, here I will see the time spent in just MPI calls. But here, besides the MPI calls, I can also see events that show me how much time is spent in at the statement level. Well, I can do that at the resolution of file or function or line. Line is the default, but if you want to generate less data and don't want to get overwhelmed, you can say -ebs resolution equals function, and then you will see the time spent in all the functions of the user application along with MPI and also OpenMP over here. So if you want to use different configurations of Tao, you have a tag which allows you to select between multiple ways in which Tao was configured, and you can say -t, MPI, PDT, PAPI. PAPI is the hardware performance counter library, and here I am saying track IO calls in the code as well. If I want to track OpenMP calls, I can just say OMPT, and then we have support for like TR7, V5, TR6, older versions of OpenMP. But in this case, Intel compilers, Intel 19, do support the OMPT standard. So for the demo, I will show you the real OMPT version 5 working with Tao. But you have to enable it with OMPT, V5 with MPI, and so on. You can also track memory leaks. You can load other wrapper libraries using TaoExec, and so on. But what key takeaway over here is you must generate a dynamic executable. How do you do that? In the link line, you just add the -dynamic flag, and it creates a dynamic executable. You must compile your program with the -g option if you want to see the symbol information that shows you the statement line numbers. Okay, you do need to have the -g, and then use TaoExec while launching the application. So you say module load Tao, it internally will load this Intel latest compiler. You don't need to really do this, but I've just shown you this. And you can untar the workshop tarball, go to this workshop directory, do a make clean, make sweet, and then in a second window you can essentially use the qsub command. It's written in the bin directory readme file, and just load the Tau module. It will internally unload Darshan. It will load the correct Intel compilers. You can use the OpenMP number of threads, run this application, and so on. I'll just go through this step by step and show you how to use Tau on a simple application. Okay. So here, maybe. So let me just make a directory and say TaoExec soft perf tools tau workshop.tgz. Okay. Here I say module load tau. I have loaded the tau module, and I go to the workshop folder, to the mz directory, and say make clean and make sweet. Okay. Let me also open up another window. And let me get a single node. You have all done this, right? You can use the account ATP ESC 2019 and use the queue R, the reservation r.appsec 2019. I'm just requesting a single node, which should be enough for this running this job. Okay. And what I want to do is I want to run this application on a single node, maybe use 64 cores, and I have created the Nass Parallel benchmark BT example. You can see that it's compiled with the -q OpenMP, and it uses optimized execution. And full optimization flags are used. And I have in the bin directory a README file that shows you how to use Tau. So this Q command, the qsub command, is documented here in the bin directory. You say module load Tau before you use it. And I was hoping that we would get the node. If you're using more than one node, maybe you can release one. And I'll get in. No? I'll try another account. So let me tell you a little bit about this application while we are waiting for the nodes to. Do any of you have the nodes? Are you able to get the nodes from this reservation? Yes?
I'm still waiting.
So you're still waiting. So still waiting, you're not able to. You got one. Lucky you. Okay, so this is a standard Nass Parallel benchmark. I just want to pick something that you may be familiar with. Just a show of hands, how many people here have heard of or used the Nass Parallel benchmarks? Okay, well, BT is a fairly common benchmark, and we can, it's written in Fortran, it uses MPI with OpenMP. You can specify the compiler name in a make.def, and so on. Oh, there. Good. I got in. Okay. So I have the login node where I can run my interactive GUI tools, and this is the compute node, mom node. So I can say module load tau here, and now I have TaoExec in my path. Okay. So if I go to the Scratch ATPSC workshop directory and go to the MZ bin directory, I have the BT executable. Now I can set the number of threads that I want to use, say 4 threads times 16 ranks in this file called, say, R. But I need to be a little careful over here. I say that OpenMP number of threads is 4. I also set the -cc depth parameter over here. I can set the number of hardware threads per core, specify the OMP num threads over here, and launch this task. Now you've covered this, right, in your previous session. Do you all feel comfortable using theta, whether it is to compile the code, launch using the app run command? And now you can see that it passed the 4 number of threads to your application, and it's running on 64 threads total, 16 MPI ranks times 4 threads. And you see, you use the CC depth for the affinity parameter, and you're able to run this. Now you're wondering that 64 threads, fully optimized O3 with the latest Intel 1903 compilers. Where is the application spending its time? What's happening, right? So you can see how long did it take? It took about U time 494. Here it says it took time in seconds, about 34 seconds. Was this a good use of the resources? Did you use 64 threads well for the B problem size? We don't know, right? Because we just run the applications. It would be useful to check where it spent its time. So let me show you another script, say RT, where instead of this app run using exactly like that, I'm going to use TaoExec before the name of the executable. And then I'm saying use the tags of version 5 OMPT, enable the OMPT support, also enable the event-based sampling so that I can see what happened in the rest of the code, and run this BT benchmark exactly like this. This is uninstrumented, this is with instrumentation. And then you can use pprof as a tool, or on a login node, not on the mom node like this. You can launch paraprof or even pack the files and then take them to your laptop. So this file, RT, will allow me to instrument the code and then measure its performance. So here, if you notice that when we actually compiled the code, we use the -q OpenMP flag for OpenMP, and then at the end, I use the -dynamic flag while linking the application. Okay, this -dynamic flag is really important while linking so that you can use TaoExec to then preload the application with the Tao shared library. So what is important is MPI remained the same. The compilers remained the same. The executable remained the same. There was no change to the source code, the configure scripts, to the executable. Everything is the same. Just the launch script now says app run, TaoExec, parameters, in or out. Okay? And now it again completed the execution, and I will be able to see the profile files over here. So one of the things I can do is I can just say which paraprof, and either launch paraprof directly like this, or I can say paraprof -- pack and give it a name. Say in this ppk directory, I can call it something like bt OpenMP theta.ppk. Okay? And here on my laptop, I can create some ATP ESC19 data directory and say SCP theta ppk and bt OpenMP theta.ppk and bring it over. So now I can use paraprof locally instead of doing it, launching it over X Windows. I have installed paraprof locally, but you could launch it remotely over there as well. And now as you see, there are 4 threads in each rank, and we have 16 threads, 16 MPI ranks with 4 threads each. I can go and say show options, don't stack the bars together. Each of these is a function, and I can click on a node over here, and it will show me what's happening in that thread. So if I clicked over here, it shows me that out of the total time, it spent 17 seconds in a function called schedule yield. It spent all this time in OpenMP work loops, xsolve, ysolve, zsolve. It spent 7 seconds in wait all. That doesn't sound good. That doesn't sound good at all. Let me see what happens on all the threads. And look at this. Out of value as percentage, as much as 86% of the time on thread 2 on node 12 was spent in schedule yield. Okay? Right down to 38%, it's spending a lot of time in just schedule yield. If I want to see other views, here is a call path relations window where I can see where time is being spent, and it says out of the 17 seconds on this rank, 2.6 seconds came from the barrier implicit OpenMP sync over here. In the xsolve routine, 4.6 seconds came from the wait all over here. Okay, but all of this time is just wasted. It's just doing schedule yield and waits. So there's something wrong over here. I should be able to do better than that. Okay, and if I look at a web page on running the codes, if I say ALCF theta running codes and say CC depth, here is a running jobs on theta. Okay, so let's see. We have CC depth over here. We have the number of ranks for MPI applications. It's good that you're all paying attention. And here is -D. This specifies the number of hardware threads to assign to each MPI rank. Okay? A lot of time is being spent in just moving the thread from one, the execution from one thread to the other. It's just going between the CPUs. But I can add this -D parameter and then generate the data. So here is a second file called RT1 where I've added the -D as the number of OpenMP threads that I had forgotten. And you can see over here, this specifies the number of threads to assign. So there's no change in the binary here at all. Let's play with this option and see if it helps us. And I can remove the profile files here and say RT1, unable to use because it's a different window. Here, RT1. So now we are running with the -D, the -CC depth, and the -J options. Again, 64 threads. But let's see how long it takes this time. And it just took like 9.7 seconds. So if I were to just pack this and say, what name did we give before? BT underscore OpenMP theta. Okay. And I say PPK. And let me give it a different name, say with D. Okay. And let me just bring this file over. And say paraprof star.ppk. So I'm loading both the files together. And this will bring up both of these files. And I can look at a particular file, say add it to the comparison window, and then go to the other one and say add this file to the comparison window. And you can see the difference here in schedule yield disappearing. If I go and say instead of inclusive time, show me exclusive time, show me the inclusive time, you can see that instead of 44 seconds total, the application now executes in 10 seconds with no change in the executable, and all of this time in schedule yield goes away. Okay? So this is just using Tao to compare the performance. You may want to say what actually happens in the code and say show me the thread statistics table, and it's showing you where the time is being spent. So in this case, here, the application is spending so much time over here. This is the optimized one. And you can see the thread statistics table. You can click, and this is a window where you can just click on it and see the time spent in different code regions. So out of the 10 seconds in the code, it says 2.7 seconds were spent in this work loop at this location in the source code, at line number 52 in ysolve.f. And you can open that up, and you can open up the files and see exactly how much time was spent on different core counts and different threads of execution. So this is the time spent, which is exclusive time. And if I say, show me the inclusive time, then it will show me that about 3.4 seconds was the max that this spent at line number 54 in xsolve.f in this loop. And this loop name comes from the OMPT interface. Okay. So let's look at this function bar chart. See the inclusive time on this thread and show thread statistics table. So here it is the time spent in the xsolve, this one, 2.3. And here we can then go down and see exactly what happens at each line in the application. Like this, line number 304, 212, and so on. Now you can also say, show me the source code, but in this case, the source is on theta, so it will just say, bring the source over and then I can show you the source file and so on. Okay? But what I'm trying to show you over here is that you can characterize the time spent in the application functions. You can see how much time was spent in the code and then compare it with where the application is spending its time at different OpenMP regions. And you can also see what happens inside the application functions. Like if there was a wait all, for instance, and you wanted to see what was going on inside the wait all, okay, you can see that these are the functions that are called inside the wait all. So I do not have the source code of the Cray MPI, right? But I can still see which functions were called inside the wait all. There's a function called poll active F boxes. There's a MPI du schedules are pending or wait all implementation or MPI wait all sample, and exactly which libraries they come from. So those names can be informative. They can tell you where the application is spending its time. So if you had an application where it was referencing some other library and you wanted to see what was going on inside that library, you could see that using the sampling over here. Now I have many other examples in the workshop tarball that you can look at, and there's a README file that explains it. I just wanted to show this demo and show how you can use Tao to compare the performance of two different parameters in the system. And you can also use source instrumentation to build the application, where you can use TaoExec for uninstrumented case or use the compiler scripts to instrument it. And this is the thread statistics table that I showed you. And you can choose to generate different types of performance data, including call site profiles, which show you where time is spent at a given location, phase profiles, call path profiles, and the flat profiles that I just showed you. And you launch it with paraprof. You can unstack the bars. You can see where it's spending its time. Here is a flat profile. Here is a profile that includes events over here, where you can see the samples. And here you can see the time spent in the application function, exclusive and inclusive. And what it's saying is that exclusively 9.1 seconds were spent in the rest of the code, but sampling can only account for 9.0 out of that 9.1. It's close enough, but if you add up the time spent in all of these functions and the source lines, then you will come up to like this number, which is in the context of the .tau application, a top level timer. And then you can see samples at a given point in the source code where the line number is shown over here. You can see how you can unwind the call stack where you get the sample. So you can see the full calling context and see a full slice of the runtime and which libraries were calling what function, and see even inside the system functions like this. You may not have access to the source code, but you can see the names of those functions by setting these variables like this and unwind the call stack. Here is a call site profile. Here is the call path thread relations window that I showed you. And you can see where that particular function gets called in its parents. You can see I/O performance data. This is the 3D visualizer that you can use. We may have some time to show you this in the workshop hands-on section. And you access this through Windows 3D visualization, where we can see the names of functions, MPI ranks, and the time spent in those functions along the z-axis. And here is a given node. And I will not go into the source instrumentation other than to say that you can just set a Tau makefile environment variable to a configuration, and then you can choose these compiler scripts to source instrument your code. This is how you can install Tao on your laptop. And if you look at a Tao directory, you can see the stub makefiles that show you which configurations have been configured, whether it's GNU with pthread, or MPI with Intel 19 compilers with pthread, or OMPT. And then you can choose one of these configurations and use the compiler wrappers. And the same tags are also available in the TaoExec command with the -t parameter. These are some other environment variables you can set in Tao options to change the behavior, such as use the compiler-based instrumentation, and have a filter file. And I am kind of out of time here, so I will just take this moment to say that these are some runtime environment variables in Tao. And you can see this at the end of the slides. You can download Tao from this location. We have extreme scale scientific software stack, which includes containers for HPC. It includes tools such as PAPI, HPC Toolkit, and Tao, all within a containerized environment available from e4s.io. Our development occurs at the University of Oregon. We have a very strong visitor program. Do consider coming and visiting us, maybe work with us for a few days, and get your codes instrumented and running if you would like. I would like to thank our sponsors, the Department of Energy, Argonne National Labs, the Exascale Computing Project, the Office of Science, the Tri-Labs, Los Alamos, Livermore, Sandia, Lawrence Berkeley National Labs, PNNL and Oak Ridge National Labs, Department of Defense, National Science Foundation, NASA, CEA in France, and our partners at the University of Oregon, Ohio State University, the developers of MVAP H2, Paratools Inc., where Tau Commander is being developed, Tennessee, Knoxville, the developers of PAPI, TU Dresden, the developers of Vampire, and Jülich Supercomputing Center in Germany, where they develop tools such as Scorpy, Skalaska, Opari, and thank the ECP project. And we'll have some time for the hands-on, and you can take the workshop Tarball. Will be available, both John and I will be able to help you if you have any questions. Thank you.
So any question? So does Tau support the GPU now?
It does. So we support both NVIDIA as well as AMD and other GPUs.
Intel later.
Yes.
Okay. So yeah.
So when you profile the kernels that are launched on the GPUs,
Yes.
how do you get the timings for the kernel launches, especially because they're asynchronous?
So that's a very good question. You know, with AMD, with ROCm and HIP runtimes, we have access to a variety of different layers at which we can instrument the code. We have tools such as Rock Profiler and Rock Tracer that can give us precise timings on the GPU for the kernels, and also the data transfers that take place from the host to the GPU, and we are able to get all that information. This is very similar to what we can get even for NVIDIA's CUPTI interface, the CUDA Profiling Tools interface, where you can see exactly when a kernel started, on which GPU, how many cores it used, and then we get those timestamps, and then we can generate the data. We can also look at hardware performance counter data from the GPU, and also the data from the CPU as well. So.
Okay, so we don't have to do a specific explicit CUDA device synchronization.
So you do not need to change your application if that's what you're asking. You just take the application, launch it with TaoExec-CUPTI, or in the case of AMD, it would be TaoExec-ROCm, and then you'll be able to generate the data. Thank you. Any other?
Yeah, any other question? Okay, otherwise, thank Samir again.